Hi, this is the atomic structure and periodic table reverse the classroom. Now, basically what reverse the classroom means is you're going to do this exercise and look at this video before you actually study the topic. So when you actually get to the topic itself, you've got a bit of an idea about what's going on. So this is then the route through the unit itself, starting with atomic structure and the periodic table, which is the name of the topic. And then what we then do is we go through the snaky diagram right the way to the end. There's a couple of little bits in it, so transition metals is then triple, but the vast majority of the stuff is stuff that you need to know. Right, the elements themselves. If we just look at sodium, we've got a number at the bottom there, and we've got a number at the top there. The number at the top, the 23, is called the mass number. And what that is the number of protons added to the number of neutrons. The number at the bottom is the atomic number. And what that's the number of protons or the number of electrons. Okay, and what you'll often get asked to do, you'll often get asked to write down the pen, protons, electrons, neutrons, so protons, electrons, neutrons. So the number of protons is 11, the atomic number. The number of electrons is always the same as the number of protons. Neutrons is protons, which is 11, added to the number of neutrons equals 23. So N will then be 12. That's the number of neutrons. Electrons. Now what electrons are is electrons are found in shells. You've got the nucleus in the middle, right, which is your protons and the neutrons. Around the outside, then what you've got is you've got the electrons in shells. Okay, now the way this works is the very, very first shell, right, it only ever contains 2. Right, so if you've got 7 electrons, what happens is electron number 1 goes in, electron number 2 goes in, and then that shell is then full. And what you then do is you draw another shell. Okay, so then what you do is you draw another shell. Right, and if I said before you've got 7 electrons, what you've got is you've got 1 there, you've got 1 there. So what I've then got is I've got 5 electrons left. When those 5 electrons come in, what I've got is I'm going to put 1 there, I'm going to put 1 there, I'm going to put 1 there, I'm going to put 1 there. So that's 4 gone, and then I'm going to put another 1 there. Okay, so that is then your 7 electrons, which is 1, 2, 3, 4, 5, 6, 7. Now the reason why I kind of spread them out around the outside like that is just to make it much clearer about where they are. All right. The second shell will take a maximum of 8. Once it gets to 8, it's then full. The third shell will also take a maximum of 8, then it's full. And once that's full, you then get to a fourth shell. Now on my diagram here, what I've got is I've got 2. All right, now the reason why it says 2 there is because that's calcium. Right, calcium is the biggest one you're probably ever going to get to draw. Now realistically, in the fourth shell, you can actually have a maximum of 18. Right, some definitions. An element. An element is a substance made up of only one type of atom. So Na is an element, and it's only made up of sodium atoms. A compound is a substance made up of 2 or more atoms, but the key to this now is they are chemically bonded together, so they are stuck together. A mixture is 2 or more again, but they are not chemically bonded. So what I can do is I can separate them out easier than in a compound. Some other words: solute, solvent, and solution. All right, so if I think about sugar in water, okay, so if I've got dissolved sugar in water, the solvent is the water, because that is then the liquid that the solute dissolves in, right? So the solvent is always the liquid. The solute is then the substance being dissolved. So the sugar is then the solute. So the solute dissolves into the solvent, and when you've got the whole mixture together, which is the solvent and the solute together, that is then called a solution. So my cup of coffee right? What it is, it's based on water. So the water there, okay, and then what I've got, the solutes that are in it is coffee and sugar. And then the whole thing is then like a solution of coffee. Now what we're going to do is we're going to go through 5 separation techniques. Okay, distillation, evaporation, crystallization, chromatography, and filtration. So the first method we're going to talk about is filtration. Now the definition of this, it is a separation technique used to separate insoluble solids. So a good example is sand and water, or you could just have dirty water with bits of grass and things like that in it. And what you do is you put your mixture into the filter funnel that's got filter paper in it, filter funnel and filter paper, and what you do then is you get water coming out of the bottom, which is your filtrate, leaving the insoluble sand in the filter paper. Now the example I've got on here, right, and I'm actually going to change my pen to black, is where I've got excess copper oxide. So what I've got is I've got a beaker, and inside there I've got copper oxide, right? I've got copper sulfate in there, and I've got copper oxide at the bottom, right? Solid black copper oxide. So what I do then is I pour the whole mixture into here, the filtrate comes through, and left in there is my excess copper oxide. That's filtration. The next one is evaporation. Now you've got to think about the words that I was using before. Evaporation removes a solvent, which is the liquid like water, from a solution, leaving behind the solute. Right? So if you think about it, let's say it was sugar and water. The solution is the sugar and the water. The solvent is the water, because that's the liquid, and the solute is the sugar. Okay. Now, the example I've got on here, right, so what we've got is we've got our Bunsen burner, we've got our tripod, we've got a beaker with boiling water in it, and then we've got copper sulfate solution. So that copper sulfate is in fact pretty much that colour. Okay, I'm not very good at colouring in. Okay, and what happens is you heat it up, right, and often what you'll do is you'll just put the evaporating basin straight on the Bunsen burner, but the problem is it then does it very, very quickly. And what happens is the copper sulfate boils, and off comes your solvent, which is your water, and then what you are is you're then left with your copper sulfate left in the evaporating basin. Now the reason why this has then got a beaker underneath it is just to do it a bit slower. So what happens is this water here boils and it heats up the evaporating basin much slower. Right? It's a bit like when you're sort of melting chocolate at home where you put it over the top of a saucepan. Okay, so that's evaporation. Now, crystallization to me is very, very similar to evaporation, where what you do is you start off with your solution, right? You filter it, but then when you actually get to the crystallization process, rather than literally boiling off all of the solvent, what you do is you put the hot liquid into a dish, and then you leave it. You might leave it overnight, and instead, what you have in here, you have crystals. Right, so really it's a bit like evaporation, right, but it's a much kind of slower process. Distillation. All right, now distillation is where you've got two liquids with different boiling points, and what you want to do is you want to separate them. Now I don't particularly like this one, so I'm just going to scribble out salt water, and what I'm going to do is I'm going to put ethanol and I'm going to put water. Right, so basically what I've got there is I've got alcohol and I've got water. So it could be like, it's like a bottle of wine, right? And what you do is you put it into there. Then what you do is you heat it up. You heat it up, do that in red, heat it up with your Bunsen burner, right? And when it gets to 80 degrees, which is a bit kind of weird, right, it then starts to bubble. Now the reason why it bubbles at 80 degrees C is because the ethanol has a boiling point of 80 degrees C. So what you do is you see the vapour of ethanol coming off. That vapour of ethanol then goes up into here, and it goes down this tube, and it goes into here, which is called a condenser. And what a condenser does is it cools down the liquid in the middle, because all the way around the outside it's got nice cold water, so it cools it down. Then what happens? Behind my head, the alcohol forms here as a liquid, and it drips out, which is called distillate. Chromatography. Right? Chromatography is used to separate mixtures of chemicals by their solubility. So what we have along the bottom here, we've got a dot, we've got a dot, we've got a dot, we've got a dot, and then we've kind of got an unknown one, which could be, I don't know, orange. Then what you do is you put it into the solvent, and the solvent takes the different colours up the page, right? So up the piece of paper, so what they do is they travel up, okay? And the further they travel, the more soluble they are. Now, this is then a typical kind of practical that there could well be. Method to separate water, sand and salt, right? So what you do is you've got your mixture of salt and sand, right? And then what you do is then you add it into water. So then what you've got is you've got a solution that's got the salt dissolved in it, and then you've got sand at the bottom. Number 3 is filter the sand. So what you do is then you'll get sand in your filter paper, and you'll get salt solution at the bottom. Then evaporate, and when you evaporate it, eventually all you'll have left at the bottom there will be your salt. So now what we're going to do, we're going to go through the development of the atom, right? 6 blokes. First bloke is Democritus, right? Now what Democritus was, he was probably 2,500 years ago, and he came up with the principle of atomos. And what atomos means, it means cannot be cut. So he then came up with atomos, which is where atom comes from, where something cannot be cut. John Dalton's idea, right, development of the atom, was he thought that an atom was just a solid sphere, okay, which is quite often what we will then end up drawing. J.J. Thomson, he was then the first person who kind of started adding a bit of detail, right, and he came up with the principle of the plum pudding. And in the plum pudding, right, what there is there's negative bits, which is like the plums, so it's a bit like a Christmas cake. And then around the outside of that, there's then little positive bits, right, which is kind of like the doughy bit. Right, sometimes it's thought of like a chocolate chip cookie, where the negative bits is like the chocolate chips, and then the dough of the biscuit is then the positives. Now Rutherford, he's kind of a guy that made massive steps, right? And what he did is he came up with an experiment called the gold leaf experiment. He came up with a principle, and we're going to deal with this a little bit more detail in a couple of slides' time. He came up with the idea that an atom was mostly empty space, it had a positive centre, and that the centre was fixed. Bohr, right, I don't know how you actually pronounce it, but I'm going to say Bohr, he came up with the idea that electrons are in shells. And the final guy, James Chadwick, right, he noticed that the whole atom itself was lighter than it should be, or heavier than it should be rather. So he then came up with a principle that there were neutrons present. Right, now this is then the one that I was then talking about before, which is then Rutherford's scattering experiment. Okay, now what Rutherford did is he had a source of alpha particles. Those alpha particles, right, are positive 2 in charge. And what he did was he shone these alpha particles, right, at a piece of thin gold. And he noticed that some scattered, most went straight through, and some were deflected. Right, so he then came up with some conclusions. A, they pass straight through. So if I look at A at the top diagram, that alpha particle goes straight through. So if that alpha particle goes straight through, what he then thought was, it's mostly empty space. That was his first conclusion. B, he noticed that some of them scattered, okay, which is basically changed direction. So this one here, it went down here, and what it did, it slightly changed direction. He knew that the alpha particle is positive 2, so he then worked on the assumption that there was a repulsion force from the middle, so he came up with a principle that the centre must be positively charged. And the third one is then some of the alpha particles were deflected, so they bounced back, which is C, where they went in, hit something and bounced back. Okay, and he came up with the principle then that there was a solid nucleus. Right, an isotope. Right, isotope is, if I just draw, I'll do 7, 3 lithium, right, and then we could have 8, 3 lithium. They are isotopes of each other. It is the same element, so it's both lithium, right? They have the same number of protons, but if we do PEN, this lithium has got 4 neutrons, because we do 7 take away 3, and this lithium has 5 neutrons. So an isotope is the same element with the same number of protons, but a different number of neutrons. Okay, why is chlorine's atomic mass 35.5? Okay, now what you've got is you've got a sum that you work on here. Chlorine has got 2 isotopes. Chlorine 35, there's 75% of it. Chlorine 37, there's 25% of it. So what you do is you kind of almost like do a mean. And to work that out, you do the 35 multiplied by the percentage, add that to the 37, multiply it by its percentage, and then divide by 100. And eventually what you do is you get 35.5. This sometimes confuses people with the PEN, because what you've then got is the number of neutrons, right? You've got to then got a decimal in there, right? There's half a neutron, which obviously can't be true, right? So that then is due to the different isotopes of chlorine. Mendeleev, all right? This is then the periodic table, okay? So what we've got here is we've got 2 versions of the periodic table. We've got Mendeleev's and we've got the modern table. Now the best way of going through this is like a comparison, right? And what you have to do is in a comparison question you say something about Mendeleev's and then you say something about the modern. So just to start off with, the first one is elements are ordered by atomic weight. That was on Mendeleev's. Elements on the modern one are by the atomic number. Mendeleev left gaps. Okay, I'm not quite sure if I can draw gaps on here, so maybe a gap there, right? If I change the colour a little bit, a gap there, right? And there might be a gap there, I can't see particularly very well. In ours, or the modern one, there are no gaps. And that is one of the most important thing about Mendeleev's, in the fact that what he thought was there's gaps, and he wrote down gaps because he knew there was other elements still to be found. He also only had 63 elements, where we've got more than 100 because they hadn't been found. He put transition metals all kind of intermingled within the periodic table himself. We have then done the transition metals in the middle. And the last one that is then dead important is the fact that he has got no noble gases. So helium, neon, argon, krypton, he hasn't got any on there, where we have then got that end column is the noble gases. Now the reason why Mendeleev hasn't got any noble gases is the fact that they hadn't discovered, because they're very, very unreactive. Okay, the periodic table, right? You might get asked about the names of some of the groups. All right, so alkali metals is group 1. Halogens is group 7. The noble gases is group 0. And then there is also another group that I just mentioned previously, which is the transition metals, right, which is this group here, okay, that is then the transition metal group. Now, properties of metals and non-metals. Metals are always found to the left of the periodic table, right? So what I could do is I could draw a very, very bad periodic table, and what there is a zigzaggy line, okay, that is terrible zigzaggy line going down the side. Metals is this side, non-metals is this side. And now what metals do is metals will form a positive ion. So if I've got sodium, it will become positive, where a non-metal like chlorine will become negative. Metals are good conductors of heat and electricity, high melting and high boiling points, which means it takes a lot of energy to turn them into a liquid and to a gas. They're ductile, which means stretch, and malleable, which means they can be bent. Non-metals are kind of like the opposite. They are insulators, which means they don't conduct electricity and heat very well, and they have low melting and low boiling points, which means you don't need to put much energy into them to turn them into a gas or a liquid. Right, why group 1 metals increase in reactivity down the group. What a group 1 metal always wants to do is it always wants to lose this outer electron. There's a 1 behind there as well. Okay, I'll just do it in there. Okay, always want to lose those. So the fact number 1 is group 1 metals increase in reactivity down the group because it's easier to lose the outer electron. Now the reason for that is it's due to the size and the distance. So if I've got a positive centre on lithium and this here is the electron that's going to get lost, I've got a positive centre on the potassium and it's this electron here that's going to be lost. The distance from there to there is much smaller than the distance from there to there, which means this electron is going to be easier to lose, which is why potassium is more reactive. There is also less attraction. So from that positive there, change the colour again, that positive there to that positive there, that positive there to that positive there, right? There's stronger attraction than from that positive there and that positive there. The last reason is shielding. If you look at that one there, you've got a positive there and you've got that electron. What's in between? One electron, right? I know that's not quite the case. For this one here, what you've got is between that positive centre and that outer electron, you've got loads and loads of different electrons that could be in the way. So it's shielding. So if you're going to answer this question, what you'll do is you'll say that potassium is more reactive than lithium because it is easier to lose an electron. And this is because it is bigger, there's a greater distance between the nucleus and the outer electron, which means there's less attraction. And also, there is more shielding in potassium. Now, properties of them, right? There's only really two main properties you need to know about. Number 1 is they're very reactive, and number 2, the reactivity increases down the group. Group 7 elements decrease in reactivity down the group. Now what this is then completely and utterly the opposite of what we then just talked about. Fluorine has got a positive centre, chlorine has got a positive centre. But what these want to do now is they want to gain one to make that into an 8. So fluorine wants to gain 1, chlorine wants to gain 1. All right? And the easier it is to gain one, the more reactive. All right? So the reasons for this again is dead similar to the alkali metals, right? There is less attraction, right, between the chlorine and the fluorine. So fluorine is more attraction, which makes it more reactive. There is less shielding for the fluorine, which makes it more reactive. And also the distance is less, which again makes the fluorine more reactive. So what we've got now is we've got the properties of the halogens, right? There's 3 main properties. Firstly, they consist of a pair, right? Which means fluorine is F2, there's 2 fluorines together. Chlorine is F2, iodine is I2, well, chlorine is Cl2 rather than F2. Melting point and boiling points increase down the group. Fluorine is a gas. Chlorine is also a gas. Iodine is a solid and bromine is a liquid. So it goes fluorine gas, chlorine gas, bromine liquid, iodine solid. And also, we just talked about it before, reactivity decreases down the group. Now, why are group 0 elements not reactive at all? Right, so the whole point in reaction, group 1 metals wanted to lose an electron, the halogens wanted to gain an electron, helium is full, neon is full, argon is full. So therefore, there is no reaction because they are already happy, they've already got a full outer shell. Now, word equations and symbol equations. All I'm going to do here now is I'm just going to explain exactly the difference between them. A word equation is where you use the words. Okay, magnesium word plus oxygen word makes magnesium oxide word. A symbol equation is where you actually use the element symbols. And with that, usually what you've got to do, so you write MgO, MgO, but with that, you're also going to need to balance. Right, so now what I've done is I've just gone through all the factual information. There's quite a lot of it. you now need, in your exercise books, to write out these questions. So you write out the questions in your exercise book, and then what you do is then you'll do briefer answers, right, from the video itself. So number 1 is, what were Rutherford's 3 observations and his 3 conclusions? Number 2, name 4 properties of metals. Number 3, compare Mendeleev's and the modern periodic table, and I want you to just tell me 3 facts, right, even though I did tell you more than that. What's the definition of an isotope? And then what is the name of the piece of equipment used in simple distillation to cool down gases? Right, so you write those out and then answer those questions into your exercise book. Right, well done. Right, so what you've done then is you've done reverse the classroom. Now all those different topics that we've actually got on there now, what you're going to do is you're going to be going through them again in lesson, but now that you've been kind of exposed to them, right, you should be able to understand them a little bit better.